Section 3.5 is called an overview of curve sketching. And obviously I know that your calculator will be able to help you to verify that the graphs that you have look accurate, but it is just a verification for you. Hey, Zach, here's your paper.
Thank you.
So like I said before I turned this on, this is really just a compilation of everything we've done in Chapter 3. And some of it back from earlier chapters as well. So we're going to piece together all of the things that we've been working with to be able to use these pieces to draw a graph. And so there's some important graphical features we're going to start with. The first one is something you learned about well before you ever entered this classroom. That's domain. And in particular, while domain is really the x values you can equal, it usually involves you considering what x values can I not have. So things like denominators equal to 0. So you look for where maybe the denominator would be 0. If you have a square root, you look at the fact that you can't have a negative underneath the square root. Those sorts of things. So that's the first place we start. The second issue is whether or not we have vertical or horizontal asymptotes. Now, sometimes you do and sometimes you don't. Okay? So this isn't necessarily going to happen on every graph. Domain is going to happen on every graph, right? But asymptotes may or may not. So vertical asymptotes, remember, occur when the denominator is equal to 0. Or at least potentially occur there. And then there are those 3 cases for horizontal asymptotes that we talked about a while back. So we could have to look at those again as well if we were dealing with something with a rational function. The third thing is intercepts. Now, you may have a graph that doesn't have any intercepts. That is a possibility. A very good classic example of that is the graph 1 over x. It doesn't cross either axis anywhere. But in most cases, you have something cross at least one of the axes. So we look for where the graphs cross the axes. If x equals 0, that's actually the y-intercept, because that would be where it crossed the y-axis. And if y is equal to 0, that is the x-intercept. That's where it crosses the x-axis. And then we finally get to the stuff that we've been learning about in this particular chapter, first derivatives and second derivatives. So item number 4 is the first derivative information. So the first derivative information tells us where a graph is increasing. We look at where, oh, these are in here backwards. That's what happens when you have things going on. That should say greater than. Please make those correct. It's increasing with f prime of x is greater than 0, and it's decreasing when f prime of x is less than 0. My apologies. Right? If the graph has a positive derivative, it's increasing. If it has a negative derivative, it's decreasing. And then we also have potential places when it's equal to 0, when the derivative is equal to 0, of local mins or maxes. Now, they don't have to be a min or a max if the derivative is 0, but they could be. And we test whether or not they are a min or a max by looking at either the first derivative test, where we have those positives and negatives, right, those intervals, or by taking the values from here when f prime of x is equal to 0 and plugging them into the second derivative and looking where they're concave up or concave down. We did that in the last section, 3.4. So we've got the first derivative information that we can glean from the graph. So we can look where the graph is going up and where it's going down from this. And the last piece of information is coming from the second derivative. So the second derivative will tell us where something is concave up or concave down. So if it's concave up, it means the second derivative is positive, and concave down, meaning the second derivative is negative. And then we have places where the derivative change, or where the concavity changes. That's called an inflection point, and that happens when the second derivative is actually equal to 0. So this list is really not anything new. You've done all of these things before in pieces. In fact, we almost put some of this all together, not quite the whole thing, but some of this all together, I don't remember if it was in 3.3 or 3.4, when we were looking at drawing a graph. I think it was 3.4, last lesson, when we talked about putting some of these pieces together and sketching a graph that had certain characteristics. We're going to put all the pieces together and sketch these graphs this time. Are you guys ready to start one? Okay. Please be very aware that your space that you have on your paper is going to fill up very quickly. So if you tend to write large, try to write small. Tend to use the margins where you maybe, like on my piece of paper, notice I don't tend to write over here. I probably would have had a lot more space had I done so. So you're going to need a lot of that space down there at the bottom in order to get all the pieces of this in here. All right, so as you're taking a look at this, I want you to first be aware that the directions that I have written here have one thing different than the directions in your book. I simply wrote to graph the function completely and discuss the graph. It says as in example, and it gives you an example from the textbook. That's fine, you can use that example from the textbook as a guide, but you could also use what we're going to do here, which will be in a slightly different order as a guide. So I put these in an order that I thought made a more reasonable sense in how we sort of process through the information. The book does it in a slightly different order, so that's fine too. All right, so the first thing that we're going to look at from the list that we had on the previous two slides is we're going to look at the domain. So what can you tell me about the domain of this function? What's domain? The x values, that's not quite. So it's about the x values. Domain is about x values. And it's really, domain is actually the x values you can equal, but it's often easier to look at the x values that can't happen to make that determination. What x value am I not allowed to have here? X can't be 0 here because if it were, what would happen? Yeah, we get a 0 in the denominator. So in this particular case, we've got a denominator to consider. All right, so that's my issue for the domain. I'm going to have an x value everywhere but x equals 0. And the reason I'm not going to have a value at x equals 0 is why? What's going to be happening there instead? A vertical asymptote, and that's actually the second thing on the list. So we know that there's a vertical asymptote when the denominator is equal to 0, or at least potentially. This one doesn't reduce, right? X minus 4 over x cubed is not reducible. So the denominator equal to 0 is going to give me that asymptote. What if somehow the denominator were able to reduce and it weren't really there after we sort of did some factoring? What would be really happening in our graph there then? Do you remember? A hole in the graph. So do be aware that if you're starting with a function that's a rational function, and this is, you've got a polynomial on top of another polynomial, that you might have to factor and reduce to start with. We didn't have any of that going on here. How about horizontal asymptote? Do you remember how to find those? Yeah, we look at the numerator and the denominator's what? So we start with the powers, right, Brooks? Okay, so first we start with the powers. What do you have, Jamie? The numerator's degree is less than the denominator, so what's my asymptote? Y equals 0. Very good. So Brooks was about to tell me what would have happened as well if the denominator and the numerator had the same exponent. If the same exponent were happening, what would happen? You'd look at the leading coefficients. Good. What if the degree on top were higher? You wouldn't have a horizontal one, but you may have a slant one, right? If the degree were exactly one bigger on top, then you would want to do division and find the slant asymptote instead of the horizontal asymptote. Okay? So I didn't include that over here underneath number 2, but it is a possibility that you could have a slant asymptote instead of a horizontal or a vertical. So keep that in the back of your mind. Okay, so that's all my asymptotes. The third issue is going to be intercepts. Let's do the y-intercept first. If I'm looking for the y-intercept, what do? We let x equal to 0, but what happens on this one if I let x equal to 0? It's not defined, right, because you get a 0 in the denominator. So this one, there isn't one, because if I try to let x equal to 0, it doesn't work. Right? Okay, good. Now, how do I find an x-intercept then? Right, we set y equal to 0. Now, in particular, if y equals 0, y is the same as f of x, of course. So this is 0 equals x minus 4 over x cubed. You could either think of multiplying by the x cubed, so it goes away, or you could just recognize that if you get a 0 in the numerator, it makes the whole thing 0. So either way you look at it, this is the same thing as having the numerator equal to 0, and that solves to what does x equal? 4. So my x-intercept is 4, 0. X equals 4, y equals 0. We're 3/5 of the way through the list, right? All right, so let's do number 4. Number 4 is supposed to be the stuff about my first derivative. Now taking a look at this function, we actually saw something happen with a function similar to this last time, maybe 2 class periods ago, I can't remember. And I said there's a way to simplify this that makes it so that I don't need to use the quotient rule. Do you guys remember that one? Since I don't have any addition or subtraction in the denominator, I'm able to separate these with a single x cubed in the denominator. Now, it doesn't clean up the same way that the other one did. I have negative exponents, but it still makes it pretty simple and straightforward to take derivatives. So this is x to the negative 2 minus 4x to the negative 3. So I end up taking derivatives using just a power rule, which is kind of nice. All right, so then I do need the derivative of that. So what is the derivative of x to the negative 2 minus 4x to the negative 3? Okay, does everybody agree? Does that look good? Great. And what I want to be using this for now, of course, is to find out where it's equal to 0 and so forth. Well, it might be easier to find out where this was 0 if we actually wrote this back into that fractional form with the exponents being positive. So the first thing I'm actually going to do is I'm going to rewrite this back in the form that I just kind of took it out of. And in order to make this work easier, I guess you could say, I wrote that wrong. Sorry. It's negative 2 right there. Fix that. In order to make this work a little bit easier, we want a common denominator, just like we've seen before. You could separate them on different sides of fractions and cross multiply, but a common denominator here is pretty easy to find. We're just going to multiply the first one by x. So this is negative 2x plus 12 over x to the 4th, and I can set that equal to 0. Or I can set it equal to does not exist as well, right? So it's equal to 0 or d and e. If this is equal to 0, that's going to be when the numerator is 0, correct? So where will this numerator be 0? What would be the numerator to make the whole thing when the numerator equals 0? What would x have to be? 6, right? Yeah, if I set that whole thing in the numerator equal to 0, then x is going to be 6. So this is going to happen at x equal to 6. So at x equal to 6, I have a potential place where I have a max or a min, right? That's what that says. D and E does not exist. I'm sorry, my screen is also, just like you, I'm trying to write as small as I can. It says D and E does not exist. And it does not exist when the denominator is equal to 0, right? And we know that that's already a location where we've got sort of a problem spot. It's got an asymptote there. We do want to make mention of it as I'm doing my sign chart or something like that so that we can make sure we get all the pieces in there correctly. Because what you don't want to forget is how the pieces sort of fit together. So I'm going to use this one, and not because I have to, but I'm going to go ahead and use a sign chart to do this particular piece. And we'll draw it over here. So here's my sign chart. I'm going to put in the x values that I just found, 0 and 6. And I want to do test values on either sides of these, right, and in between. So what's a value you'd like to choose before 0? Negative 1. Between 1 and 6, I'm sorry, between 0 and 6? 1. How about after 6? 7? Okay. All right, so these are our 3 test values. Where do we test these test values? Into the first derivative. Very good. And what are we really looking for as we test them? The sign. Is it positive or negative? Very good, guys. All right, you guys are remembering a lot of pieces of these, even though we had a weekend. All right, so we're going to plug them into, and it doesn't matter which version of this, kind of like this version. Notice whatever happens in the denominator, what happens when I plug something into this particular denominator? It's always going to be positive, right, because I have a power of 4. So I'm really looking at what happens when I plug it into the numerator, right? So let's take negative 1. If you plug negative 1 in for x, you've got negative 2 times negative 1 plus 12. What do you get? Which is 14, which is a positive, right? So we're going to get a positive value here, which means it's increasing. So I'm going to draw that increasing line. What happens if you plug in the number 1? It's also positive. It's slightly less positive, right? But it is positive. So I've got another increasing piece. And then what happens when I plug in 7? That is negative, and then the graph would be decreasing there, which means what happens at 6? There is a maximum. What happens at 0? It was not a max or a min. We actually know what happens in 0 already, though. What happens at 0? There's a vertical asymptote. Yeah, very good. All right, now that's a maximum. It's just a order. I mean, it's one value for the maximum, right? It's the x equals 6 value. I am going to use this to graph, though, so it might be helpful at some point. And I'm here now, so let's do it. to find the y value that goes with that. How would I find the corresponding y value for this x value of 6? Original equation. So up here in the original equation, on top I have 6 minus 4, which gives me 2. And on bottom I have 6 cubed, which would give me, do you know what it is? 216 is correct. So if I take 2 over 216, that would reduce to 1 over 108. It's nearly 0, right? It's very, very, very small, but positive. So I'm going to be slightly above the x-axis when I do plot that point eventually. So this is my maximum that I'm going to use. It's also important to recognize that there I'm going to have the graph that is increasing between between negative infinity and 0. It's also increasing between 0 and 6, and then it is decreasing between 6 and infinity. So you can either write those out in pieces, which would be fine, or you can mark them on like the number line like I did, which still gives you that same information so that you can apply it into the actual graph later. We're all good with that so far? We have one more test to do. We have the second derivative information. So our second derivative, well, I had a first derivative, and in this case, this particular first derivative version would probably be the easiest one to use to take a second derivative, right? So what in the world would my second derivative be from negative 2x to the negative third? Right. And then how about the 12x to the negative 4? Someone else do that one for me. Thank you, Nathan. Negative 48x to the negative 5th. Okay, now we're kind of back at the same spot that we were when we did the first derivative. Our goal in doing all of these is to set them equal to 0 and see what happens in terms of increasing and decreasing, or concave up and concave down in this case. So I'm going to put that back into that fractional form. So this is 6 over x to the 4th minus 48 over x to the 5th. And on this one, I can get another common denominator, right? So I get 6x minus 48 over x to the 5th, and I want to find out where in the world is that equal to 0 or does not exist. Now the does not exist is still at x equals 0. The denominator, at least in terms of where it's equal to 0, has not changed in any function I've worked with. But where does that numerator equal to 0? It's at 8. So I'm going to have a concavity change, at least potentially, at the x value of 8 now. Okay, everybody good with that so far? I hesitate to change my screen, but I'm so much stuff on the screen. Maybe I can move this piece over. All right, I need a number line. I need a number line that includes the values 0 and 8. And I want to test values around those points. So what value would you like to use before 0? Negative 1 still? Do you want to use 1 between 0 and 8? Okay. And then after 8, just 9. All right, now keep in mind here, unlike the last situation when I had x to the 4th in the denominator, and x to the 5th in the denominator is not always positive, is it? No. In fact, when I plug in x equals negative 1, the denominator is negative. What is the numerator when I plug in x equals negative 1? It's also negative, right? Because I'm going to have negative 1 times the 6 minus 48, right? So I've got a negative over a negative, which means it's positive. So this particular one is positive here. And what that means in terms of our graph is that right here it's concave up, doesn't it? All right, let's try putting in x equal 1. Now if I put in x equal to 1, the denominator's positive. Yeah? What happens in the numerator when x is equal to 1? It's negative. So this one is actually going to be a negative over a positive. So this one's negative, which means that the graph between 0 and 8 is concave down. Last piece, the number 9. Denominator is positive, right? 9 to the 5th is positive. What happens in the numerator? It is positive on this one. So the whole thing is positive. So it's concave up. And also you see that at the x values of 8, just like we had anticipated, we have an inflection point here, right? We don't have an inflection point at x equals 0, although the concavity does change there. Why not? We've got an asymptote still going on there. Now, believe it or not, all of that information is going to be drawn inside of a graph. And that's a lot of information we just found, isn't it? But it is going to justify all of the pieces of the graph that we're going to create. So we're going to take a graph. And on our graph, apparently there are some important points. What are some of the important x values on our graph that we need? We're going to have an x equal 8. That came from the inflection point. In fact, let me go back and let's write this out. We didn't write the ordered pair that's the inflection point. We have x equal to 8. How would I find the y value? The original equation. So the original equation would give me 8 minus 4, or 4 on top. What's 8 cubed? What'd you get, Shannon? Okay. 512. A couple of you left in it. 512 look good? So we're going to have 4 over 512. What does that reduce to? 1 over what? 128. So again, a very, very small but positive number. Okay, so it's going to be above the x-axis, but just barely. Yes?
I have a question. The points you picked out, like the 6 over 1 over 108, 108, are those just points you're plotting on this graph?
I am going to plot them on the graph. Okay. The reason we're particularly picking the 6 and the 8, though, is because they came from the maximum and the inflection point. So there is a reason for picking those particular points. But yeah, I can't just plot them without knowing the ordered pair for the full location. So that's why we did that. Okay, so I need x equal to 6 in here. And 8 in here. And I don't know about you, but apparently my x values are going to be very small, so I'm going to make my scale really large on my y-axis just to try to give it some kind of a dimension here for what's going on. It's still not going to be an excellent rendition of that, but and I have a asymptote, right? So that's another important point here happening. I have 2 asymptotes. I have a vertical and a horizontal. So I'm going to draw those in a different color just so that we can see it better on my screen. I'm drawing them dotted along the x and the y-axis because one of them is x equals 0 and the other is at y equals 0. Okay, then it said that I have one other point. What about this x-intercept? We haven't plotted that, right? So x equals 4 is an important point, 4, 0. I'm going to draw my graph in blue. So x equals 4, 0 is actually across the graph right there. Now, we talked about this before, but just let me reiterate to you. It's okay to cross the asymptote. At least it's okay to cross a horizontal asymptote. Horizontal asymptote actually tells us about end behavior. That is what happens on the edges of the graph. We don't necessarily have the inability to cross a horizontal asymptote in the middle of the graph. It's just that towards the end of the graph, we have this tapering off sort of feature going on. Okay, let's start on the left-hand side of the graph, okay? Well, the left-hand side of the graph. That is, let's look at the values before x equals 0. So we don't have anything on the left-hand side of the graph at all in terms of points. We at least have one point on the right-hand side. And we know we've got 2 other points that we could plot. We could plot those 2. I guess we could do that now. The value at x equals 6 is slightly larger than at x equal to 8. They're still both very small, but there is sort of a little bit of well, it's a maximum at x equal to 6, right? So it's slightly above the x equal 8 value. Okay, so I want to talk about what happens on the left-hand side, that is before x equal to 0. So what is happening with the graph before x equal to 0 from these sign charts that we've created? It is increasing, and it is concave up. So where in the world would that graph be? Will it be above the x-axis, or will it be below the x-axis? It's got to be both increasing and concave up. Has to be above. Let me show you what happens if I try to draw it below. If I try to draw it below, it has to look like this. But what is this graph doing? Decreasing and concave down. So it actually fails on 2 accounts. So this one's not okay. But I can do the other one up here, and it is both increasing and concave up, right? That looks pretty good, right? All right, let's go between 0 and 6 now, because that's the next sort of a differentiation I've got. Between 0 and 6, my graph is supposed to be increasing and concave down. Now, I know the concavity downwards goes clear until the value of 8, but I'm just looking until 6 right now. Okay, that's still within that 0 to 8 range for the concavity. So I need to be increasing and concave down. Well, the graph needs to be increasing and approaching this particular point, and then continuing on to this particular point and concave down. So do you have a sketch in mind of what that looks like? What's it look like? Should kind of look like half of a downward parabola, right? So it looks something like this. Increasing, concave down. Now the first derivative tells us what happens after x equal to 6. What's supposed to be going on after x equal to 6? It's supposed to be decreasing. So I am going to decrease now from here. And I'm trapped by a few things. Like, it's got to be decreasing, but it's got to be tapering off at x equals, or at the x-axis, right? Because I've got a horizontal asymptote there. But also something else happens at 8. What happens at 8? It changes concavity, right? So it's actually, and it's going to be difficult to draw simply because the graph is so small, but it's going to be concave down until we get to here. And then it's going to sort of flip around and look like it's concave up after that. Now, this is a rational function. You learned about these in college algebra, maybe even in intermediate algebra and algebra, high school algebra, like Algebra 2 kind of course. You would not have been able to put this much detail into that graph because you wouldn't have known about things about concavity or increasing, decreasing. In fact, the very fact that it crossed the x-axis probably would have blown your mind when you did it because that didn't even make sense because asymptotes are things you weren't supposed to cross. Graph it in your calculators. Make sure that this is what you're seeing, more or less. Probably just a standard 10 to 10 window would be okay. How's it look? How's everybody doing? Is it looking like what you have? I got a couple of nods. Anybody's look different or look like we weren't expecting? No? All good? All right, any questions on that one before we go on to the second example? Okay, you'll be happy to know the second example is easier. There's less going on in it. This graph is a graph of a square root, right? So the first thing we talk about is we talk about domain. So how do we deal with the domain in a function like this? I mean, I don't have a denominator to worry about, right? So what do I do for domain?
We know it's not negative.
Right, we know that this, let me have you tell me, Zach, what is it that's not negative?
Oh, the x. Or inside the...
How about under? Can we say under? Okay, so the value under the radical, all of it, that is the 2x minus 1, is not going to be negative. And one way to say that is that it's positive or 0. So we can say greater than or equal to 0. And then if we solve this, we have 2x greater than or equal to 1. And then x greater than or equal to 1/2. So I'm not even going to have a left-hand side of this graph. There's not going to be anything on my graph before 1/2. Right? All right. How about, this is number 1. How about number 2, the x and vertical and horizontal asymptotes? There's not any on this one, so just kind of write down none on that for yourself so you know you've checked it. There aren't going to be any because those occur when we have numerators and denominators. They also would occur, of course, in trig functions if we were dealing like with tangent or secant or cosecant or tangent. All right, the third thing is to do x-intercepts and y-intercepts. We'll start with y-intercept. I think that's what we did last time. Our y-intercept is found by doing what? By letting x equal to 0. So if x equals to 0 in this graph, or in this equation, what happens? We get a negative under a radical, yeah, in particular. Are we allowed to do that? not with real numbers. So there is not going to be one of these. We can't let x equal to 0. In particular, why can't we let x equal to 0 by number 1? What did we say the domain was? X is greater than 1/2. Well, 0 is not greater than 1/2, so it's not even allowed, and it's not a part of my domain. So that's another reason. All right, then we've got the x-intercept, which is where we let y equal to 0. So if we let y equal to 0, in this case it would be 0 equals the square root of 2x minus 1. Of course, the square root doesn't affect that, right? If I get a 0 underneath the radical, it's the same, or you could think I'm going to square both sides. Either way, it will result in you having 2x minus 1 equal to 0, which looks uncannily like what we did earlier, except it's got an equal sign, right? So I end up with 1 equal to 2x, or x equal to 1/2. So my x-intercept is at 1/2, 0. That is, I'm going to cross the x-axis there, or at least I'm going to touch the x-axis there. All right, number 4 is to look at the derivative. Okay, so the derivative on this one is a little bit different than the last one. I don't have to do any simplification anyway. What will I have to use to do the derivative of the square root of 2x minus 1? Chain rule. Very good. So somebody tell me what the derivative, first derivative is for this. Remember, we can write this as 2x minus 1 to the 1/2. Excellent. And what beautiful thing happens here right off the bat? And the 2 and the 1/2 cancel, which is awfully nice. So I actually end up getting 1 over the square root of 2x minus 1. Everybody good with that? Okay. Now normally I want to set this equal to 0 or equal to does not exist. Well, what happens if I try to set this equal to 0?
1 doesn't equal 0, you get the same.
Yeah, so really when I've got a fraction, I look at where the numerator is equal to 0, right? And my numerator here is just 1, and there's no way to make that 1 equal to 0. So I don't get anything from this piece, that is from x equal to 0, or setting y equal to 0, the function equal to 0. And then the d and e, I get the same value I've already gotten multiple times now. I've gotten them twice before. This is, again, x equal to 1/2. And I know that I have to have a value that is bigger than 1/2 already. So in terms of the first derivative gives me no critical values, doesn't it? I get nothing. I mean, even the 1/2 is sort of not a real value because I can't have any values less than 1/2. So what do? Well, we just pick a value bigger than 1/2 and see what happens. So in particular, here's my 1/2. But I only have values bigger, so how about we pick a value 1? If x is equal to 1, what happens inside of that derivative? What do I get? 1, and I get a positive, right? And in particular, even if I hadn't sort of checked the value 1, we could talk about generally why this has to be positive. Well, I've got a positive number on top of number 1, and I've got a square root on bottom, and what kinds of numbers come out of square roots? Positive. The only time you get a negative is when you put the plus or minus on something when you solved it, right? So square roots give me positive numbers as well. So this is always positive. So that means this graph is increasing everywhere. That is, it continues to increase. So far, so good? Next is the second derivative. There weren't any maxes or mins, right? Because it never equals 0. Remind yourself that it never changed from increasing to decreasing, so there's no maxes or mins. All right, so I've got this function right here that I'm taking the derivative of, 2x minus 1 to the negative 1/2. What will that look like? It's a chain rule again, yeah? And then times 2. Very good. All right, so again, I've got a 1/2 at the beginning and a 2 at the end. The difference is the first piece is actually negative. So when I'm working with that, I need to remember that it's -1 on top. The denominator is a square root of the 2x minus 1 cubed, right? That's what the 3/2 power means. The half part means that it's over, that's a square root. And then the 3 power means it's cubed. So this graph, again, set equal to 0 or set equal to does not exist, has the exact same problem, right? That equation as the last one. The numerator is never going to equal 0, so I get nothing from this. And the denominator set equal to 0 is still going to be the number 1/2. But that's because at 1/2 is when I'm actually allowed to have domain values. So we, looking at a number line, if you want to think about it that way again, are looking at values that are bigger than 1/2. You can pick a value if you'd like, or you can do it generically. If you want to pick a value, the value 1's as good as any. The numerator is always negative. The denominator at x equal to 1 would be positive. In fact, the denominator would be positive no matter what we put into it, as long as it was an acceptable value, because it's a square root. So this graph has a negative on top, a positive on bottom, which means that we get a negative overall. And negative overall means what? This is concave down. And again, it's everywhere it's concave down. That is, it's concave down on the entire domain. All right, so, oops, with that much information, we can actually draw a graph. Our graph needs to have what points marked? 1/2. That's like the only thing that we use the entire way, isn't it? It's the only x value I got anywhere. What happens before 1/2? Nothing. What happens after 1/2? It's increasing and concave down, which means it looks something like this. Right? Increasing and concave down. Now take just a moment to graph that in your calculator, confirm that it looks like what we were expecting. Look okay? Excellent.